Minasan, konnichiwa, Zamurai Engineer. In this video, this is now the third module of chapter 3, which is about the solution of nonlinear equations. This is the third method, and therefore we already done explaining the two previous methods. We already know about the Newton-Raphson and the bisection method. So we are now in the third one, which is called secant method. Okay, secant method, how it is derived. So we have the Newton's method, wherein it is the familiar formula of the Newton's method or the Newton-Raphson method. Xi is equal to Xi minus Fxi over first derivative Fxi. Let us use this equation to approximate the derivative. So we have this type of formula from our calculus. Definition of slope. You can also refer to the graph in order to easily imagine the equation. Slope is just tangent theta. So tangent theta is the first derivative. So tangent theta at xi, this is the point wherein we took the slope. So meaning that is the point wherein the straight line and the chord is tangent to each other. Okay, so this is the equation, meaning the numerator is the difference between this and this one. So Fxi minus Fxi minus 1. Fxi minus 1 is another value we need to evaluate, no? And the denominator is xi minus 1. Okay, so substituting equation 2 into equation 1. So this is our Newton's method from the last module. Let us substitute this value to this one, meaning the first derivative here, substitute it here. What will happen? This part will become denominator, and since this is denominator, the denominator of this will become numerator. So that's why this one, the denominator will become the numerator here. Okay, so that is how we simplify this algebraic rational function. Okay, so therefore we have this as our current equation, and this is now a formula wherein we have what? Xi plus 1, and Xi minus 1. There are three important points now. Okay, and the second method can also be derived from geometry. So using what? The similar triangle. So AB divided by AE, that is tangent. AB divided by this, that is tangent, or the slope at xi. That is equal to DC divided by DE. Similar triangle. Okay, can be written as. So take note, you have to review similar triangle in order to understand this one. This can be written as this one, because AB is just the function at xi, and CD is just the function at xi minus I, xi minus 1. What about AE? AE is xi minus xi plus 1, and DE is xi minus 1 minus xi plus 1. Look at the triangles. Then rearrange all the terms and solve for xi plus 1. Why we have to solve for xi plus 1? Because xi plus 1 is the value that will become the new scientific guess. Okay? That is the new scientific guess. Okay? So the current scientific guess is xi. The new scientific guess will be xi plus 1. Okay? That's why we have to solve for xi plus 1. And take note that the formula will be the same as the previous page. Okay, this is the second method formula. Okay, how to implement this? How to use this? How to operate this formula mathematically, this method mathematically. So let us have the procedure step by step. Step 1, calculate the next estimate of the root from two initial guesses. What are the two initial guesses? Xi minus 1 and xi. That is the initial guesses, without which we cannot evaluate all of this. So we need xi and xi minus 1 to evaluate this. We need xi to evaluate this. We need xi to evaluate this. We need xi minus 1 to evaluate this. We need xi. So there are two values that we need to guess, to initial guess. Okay, find the absolute, relative, approximate error. Okay, we are already familiar with this formula since chapter 1. So step 2, after two initial guess of the value of x, let us find if the absolute relative approximate error is greater than pre-specified relative error tolerance. So because this is what? This is our stopping criterion. We will know when to stop if this specified relative error tolerance is greater than our calculated absolute relative approximate error. So we will stop the algorithm. Also check if the number of iterations has exceed the maximum number of iterations required. For example, if this requirement as 10 iteration. On the last module, we showed you that there are examples that needs about 18 iteration. Okay, so just be brave. Okay, be industrious. You have to be industrious. If you are working for down the toilet company, okay, name of the company that makes clothes for ABC commodes, okay? The floating ball has a specific gravity of 0.6 and has a radius of 5.5 centimeters. You are asked to find the depth to which the ball is submerged with floating in water. So this is the same example that we used in order to show the effectiveness of bisection method and the Newton-Raphson method. So let us tackle the same problem. We have the same given equation, which is fx equal to x cubed minus 0.165 x squared plus 3.993 times 10 to the negative 4. Use the second method in finding the roots of the equation. It is the depth x to which the ball is submerged under water. Okay, let us take note to conduct 3 iterations to estimate the root of the above equation. Find also the absolute relative approximate error and the number of significant digits which is supposed to be correct, okay, for each iteration. So let us go. Solution: to aid in an understanding of how this method works, to find the root of an equation, the graph of fx is shown to the right. Okay, so we have we have this graph. Okay, can you see the graph on your monitor and the corresponding equation? So let us continue our solution. Let us assume the initial guesses, because there are two. Of the root of fx equal to 0 as x minus 1, x sub negative 1 is equal to 0.02, and x0 is equal to 0.05. So there are two. Okay, those are the initial guesses. Okay, x negative 1 and x0. Okay, so iteration number 1, the estimate of the root is by using the secant method. Okay, we have the following. Just substitute for x0 and x negative 1. Just substitute all of this. Okay, and use the equation fx and substitute the corresponding. For example, x negative 1, you have to substitute to the equation fx. Okay, doing that and simplifying, we have the xi, the value for x1. The value for x1 is now equal to 0.06461 meters. That is our x1 after first iteration. And solving for the absolute relative approximate error, epsilon a, at the end of the iteration 1, we have what? 22.62%. Zero significant digit, because that is 22.6. That is more than 5. Okay, so let us continue and prepare ourselves by imagining our curve, our graph. So in our graph, we have what? The yellow and the green as the second and first guess. Our second guess, our first guess. And x1 is here. Take note, x1 is very near to our answer, which is 0.062. Okay, take note, our value of x1 is 0.0646. So almost we already got to the answer, while having a guess, the yellow and the green one, we already found the answer. Almost. We are there almost. Just iteration 1. And let us do the iteration number 2. The estimate of the root is, therefore, let us now use the values for x0 and x1 in order to find the value for x2. Okay, in order to find the value for x2, because this is the second iteration. So doing the same thing, substituting all the required corresponding values, you can have the value for x2 as 0.06241. We know that the correct value is 0.062, and therefore we already have two significant digits. Let us confirm if we have two significant digits correct. So using this, we only have one significant digit correct, because the answer for the absolute relative error is 3.5. And this is just less than 5%. 5% is one significant digit. So at least one digit is correct, and that digit is 0.06. 6 is the correct digit. Okay. And you will notice that the yellow and the blue is almost on the same line. They almost coincide with each other. And just to inform you, the second line is the purple. This purple line, purple straight line is the second line. And take note that there is a second relationship because this purple line intersects the curve at 2 points. Here, 1 and 2. And because of that, that is the definition of secant line. That's why this method is called secant method. So this is for iteration number 2. And let us find out what if we do the iteration number 3. Doing the same thing, but now using the value x1 and x2 in order to solve for x3. Okay, so substitute the values for x1 and x2 to the formula. So we have the result x3 is equal to 0.06238. Okay. So very near to the, and as you will notice, the absolute relative approximate error could be calculated and it became what? 0.059. Okay, the number of significant digits at least correct is 5. As you need an absolute relative approximation of 0.5. Okay, so this is not correct, no? 0.5, therefore, if the answer is 0.5, 2. The significant digits correct is 2, not 5. Please correct this. Please take note. Correct your notes here. The number of significant digits at least correct is 2. 2, not 5. Okay, because our answer here is 0.059. Which is less than 0.5 because our criterion is 0.5 for 2 significant digits. Okay, so at least we know that the correct answer is 0.062. Okay, and this is the graph showing that. Look at the secant. The secant line is now looking like a tangent line. It's not the real secant line. It looks like a tangent line. Okay. What are the advantages of this method? It converges fast. Okay. If ever it really converges, take a look between Newton-Raphson and this one. So Newton-Raphson converges faster than this one. And also another advantage is that it requires 2 guesses that do not need to bracket the root. Unlike the bisection method, we need 2 guesses that on the other side of the goal, on the root. That's why we need to, in the bisection method, you can recall that we need to use the 2 guesses, and if you evaluate the function using that value, if you multiply, it will become negative because they are on different side of the roots. But here, we do not have to be on the different side of that because this is secant method. Okay. And what are the drawbacks then? One drawback is this one, which is you will notice this is what? A sinusoidal function, which will always give us problem because sinusoidal function is a periodic oscillating function. It oscillates 0, positive, negative, 0, positive, negative. So it continues up to infinity. That's why it will always give us problem. Okay. However, we can still find a way to solve this. Okay. So one of the drawback of the method is this one. If you choose the blue and green intersection points on the curve, there will never be a time that you can find even a single point that would satisfy fx is equal to 0. You cannot find any roots of the equation. Okay, that is one drawback. Division by zero, and also what? Root jumping. The roots are jumping from, this is the green and the blue are our guess. And instead of being able to determine the nearest root, we are nearing the what? The other roots rather than the nearest one. So it jumps to different roots. Okay, so jumping roots. Okay. So that is our advantages and disadvantages of this method. And if you can recall, there are also advantages and disadvantages of the other methods. So in this chapter, we are able to introduce 3 methods in order to solve nonlinear equations. So finding the roots of nonlinear equation using numerical solution. So we have what? Bisection method, Newton-Raphson method, and secant method. Okay. Again, this is Dr. EYPEI, preaching engineering for nation building.